Okay. Unfortunately, the end of last lecture was cut by YouTube, so we may need to re-upload it, but you have the notes anyway. So last time I make some summary but didn't write it out, and there is one in the paper, but here I only have the operators, and I want to have also the not only the operators but their properties. So I will make a table comparing smooth exterior calculus to combinatorial mesh calculus, and we'll use these properties for deriving various weak formulations for transport phenomena, which of course various weak formulations for transport phenomena, which of course is the goal of the goal. There are two main goals. First is to develop the calculus, and second is to show the calculus, both smooth and discrete calculus, on a particular physical problem, in this case transport phenomena. So let's say summary of exterior. This will be short, the summary calculus. Let's call this EC, and combinatorial mesh calculus CMC, and then transport phenomena. Of various formulations. With EC and CMC. Okay, this is what we'll do today. So let's start with some table. So I will have here first operations. So, and then I will have rules. So here I have first I have table of operations and then table of rules. So first table of operations. So M is okay. Before that, let me just before that define what the setup is. So we have setup M G smooth oriented compact smooth manifold, and K with mu is oriented, compatibly maybe, but only oriented. This will be fine. Okay, last time I didn't say, but in theory, a mesh can be infinite. For example, if you have infinite region, you can have infinite grid. But we're looking with bounded regions, so our meshes are finite. Finite Riemannian mesh, and D, of course, is the dimension of M, and is the dimension Riemannian quasi-cubic mesh. And this is usually so it's partition of M. Okay, and D is the dimension of K. So first we have now this is our setup, and I do the table of operations. So first table of operations. I will use upper index K if the name is the same for smooth and exterior, just to distinguish them. I will show what I mean. So first here I have exterior calculus. And here I have combinatorial mesh calculus. So we have D operations and I don't know, spaces maybe. And spaces. It's better to swap it spaces and operations. So we have here we have there is some analog, but I'm not going to do that. But here we have C bullet of them, which is the chains. These are chains. There is an analog that I didn't talk about, smooth chains, which are some. If we have a partition, we have such chains. Here I'm K, sorry. But let's now take to the forms. So we have omega bullet. These are forms. And C, K, these are cochains. I have wedge product. So wedge product omega Pm times omega Qm to omega P plus Qm. And its analog is the cup product. So CPK times CQK to CP plus QK. I have the exterior derivative, which is from omega Pm to omega P plus 1m. And here I have the co-boundary operator. Here dp from cpk to cp plus 1k. Then I have integration. So integration over m. This takes a form, a D form, and returns real number. And here we have what I described last time. We have like I would call it so we have, maybe I call discrete integration, but I'm not going to use this terminology later. But so I have from CDM to R, and here integral over M of sigma is just sigma with the fundamental class. So recall that the fundamental class M is the sum of all these cells. C in KD, C, C, the sum of all chains, D chains, D chains. And now let's go to metric operations. So metric operations. These are again, so we have the we have a metric tensor that we don't have in 2Fn. So we'll have metric tensor, but then we get inner product. So we have inner product. This is of two arguments. And we have an inner product here as well. Okay. And then maybe I can put that this is on K. And this is from CPK times K to R. From inner product, okay, we have Hodge star. Now there is a bit difference that the Hodge star is usually done directly from the metric tensor in the smooth case, but so here doesn't happen. But here it's done from the it's defined using the inner product, but the domain is the same. So this is CPK to CD minus. And finally, we have here we have maybe this is okay. We have the cobound, not the cobound, the codifferential, this star P from omega P n to omega P minus 1 n. While here we have the joint coboundary. Omega P n, omega P minus, sorry, this is K. C E K to C P minus 1 K. I will erase all of this. And now this is what we have as operations. Now let's see what rules we have. So two rules. Equalities. Okay, equalities. So we have here exterior calculus, EC and CMC, not to write it. So we have the so-called graded anti-commutativity. So omega OH eta is -1 to the power of PQ eta OH omega, where eta is in omega Pm and eta omega is on P and eta is in omega Q. And here we have similarly that sigma small with rho is -1 to the power of PQ rho small sigma. Again, sigma is here is a cochain and rho is a Q cochain. We have the graded Leibniz rule. Which says that the omega wedge eta is the omega wedge eta plus -1 to the power of p omega wedge d eta. Doesn't matter what it is, but omega is a p4, so omega is a p4. And we have the same here with the boundary operator. So delta rho is delta sigma wedge product with rho plus, so here the operator is applied first, plus -1 to the power of p sigma with delta rho. Here sigma is a p4. We also have I forgot to talk about the trace. Anyway, it's not that. The integral of omega, not omega, over m of the omega is integral of the omega of here the trace of omega. Okay, trace of omega. Here omega is a d4. And here we can write this operator. So sigma applied, I didn't talk about that last time, but it's not very hard to show that sigma applied at the boundary of M, boundary of the basis of this thing here. So this is the fundamental class, and we take boundary. Here is d -1, so not d4. Is the same as, no, not I want to have the same order. So delta sigma applied at the fundamental class is sigma at d of m, which is this thing here. And here sigma is at d -1 for. This is just the definition of the co-boundary operator and the dual of the boundary. Okay. And now let's put the metric. We have some relation with between inner product and Hofstad, and this is oh, thank you.
And sigma is in the C d -1 here. On the left side, right side of that. Overhead.
Where?
Go up overhead. Yes.
Are these M
This is K. Okay. You should tell me earlier. Yeah. Okay. That it's fine? No.
Yes.
Okay. Now, with the operations, we have the inner product of omega with star p of eta. Let me see, both operations are fine, but let me see how I wrote it here. Okay, I put on the first one. So, star p of omega with eta is star p of omega with eta is the integral is a p form and eta is a d minus p form. And here we have star, let's make it over k p of sigma with eta is sigma with the product with theta. Here, this was definition here. This is not definition in statistical calculus, but can be proven to be that. And so here sigma is a p form and not it, rho. And rho is a d minus p form. Then we have specifies two things. First, delta dp star omega with eta in our product is omega with d of eta. Here omega is a p form and eta is p minus 1 form. So this is the integral over p minus 1 and this is over p. And here we have, this is definition here and the definition as well in the continuum. This should be zeros on the boundary. So here we have delta star p omega sigma with a rho on p minus 1. Here k maybe, and here is k as well. This is d minus p, and this is d minus p. Inner product. And this is the same as sigma delta rho. This here is p minus 1, and this is p minus 1. Again, okay. And this is p. And here sigma is 0 on the boundary, p cochain, and rho is 0 on the boundary, p minus 1 cochain. And we have the following: delta d minus p star composed with star p is minus 1 to the power of p plus 1. This was star d minus star p plus 1 composed with D. And here we have delta star D minus P. Composed with star P. This is okay. Is minus 1 to the power of P plus 1 star P plus 1. Okay, composed with delta P. And so these are the equalities we have. We have few differences. Let's talk about them. Okay, there are two main differences. One we don't care about much, and the second one is a bit problematic, but we live with it. So three differences. So first is wedge product is associative and cup product is not wow, but cup the wedge product wedge, but cup product smile is not. And the second difference, and this difference could not be overcome. So, all the properties that we have, so all the definitions that we do in the mesh calculus are influenced by what we have in the smooth calculus. So they don't come from the sky. This is what we are trying to achieve. And Hodge star on M is invertible, and moreover star P composed with star D minus P is minus 1 to the power of P D minus P with identity omega D minus P. However, but star K is not okay. Star P is not. Well, the main reason is because since the number of P cells and the number of D minus P cells are different. And so the both spaces have different dimensions. So C P K is not isomorphic to C D minus PK. In special cases, however, we have invertibility. So what are these special cases? So this is always true. Star 0 of 1, and 1 is the identity. So this is star 0 of n1 plus n2, so on. This is the volume form, which is volume is mu of the, so this is the sum of maximal cochains with their measure. So this is sum C is the cell such that mu C with the basis cochain. So for example, in this here, F0, F1, F2, F3, we will have that volume is mu F0 times F0 to mu F3 times F3. This is the idea. This is the volume. So we have that star 1, 0 of 1 is volume form, and star Z of volume form is 1. So we have this. These properties are one of the motivations for this. So, as I said before, if we have the inner product, we have everything else canonical by these formulas here. So we have the Hodge star and the delta P. However, how to define is not that obvious, and the definition, I want to be close to approximation of the continuous Hodge star on regular grid. I want to have these two properties, and also on a regular grid cubicle, or not cubicle, a regular, okay, cubicle, maybe also with parallelepipeds, but let's say it's cubicle grid. We can form global Cochain. I will not go into details about that. Global, not global, but Cochains summing all cells in the same directions. All cells in the same directions. Call them, I don't know, E, P, and the direction will be not, let me know, sigma P, and then I want to I pi. I will explain that. So that star P of sigma P I1 I pi is plus or minus sigma d minus P, and then G1 to Gd minus P. So that, and then 0, 1, 2, 3. And this have positive counterclockwise orientation. Now, what we have is that sigma 0 is n0 to and 8. This is equal to 1. Sigma 1, we can have two possibilities. Sigma 1, 1 is sum of the direction of x. So this is E1 to E0, sorry, to E5. Or maybe we could call it sigma 1x. And then sigma, this is sigma 1, 2 is E1 plus E6 to E11. And this we may call it sigma 1y. I think I forgot to put measures. Yeah. Yeah, sorry. So I forgot here to put measure times x, let's say. So mu of E0 to, okay, I said cubical, but it can be rectangular as well. Is x and mu from E1, E1, E6 to E11 is y, and mu F0 to F3 is x times y. So this should be multiplied by x. This should be multiplied by y. This is sigma 1x. This is sigma 1y. And sigma 2, and it has to be 1, 2, because it has two. Only one direction, only one two-dimensional direction. This will be F0 plus F3 times xy. And then maybe this is sigma 2, because only sigma 2. This doesn't matter, the alternative. And we have the following. So star 0, sigma 0 is sigma 2. Okay, I will use this. Star 1, sigma 1x is minus sigma 1y plus star 1 of sigma 1y is minus sigma 1x, and star 2 of sigma 2 is sigma 0. This is like in the continuum, where we have star of 1 is dx dy, star of dx is dy, star of dy is minus dx, and star of dx dy is 1. And in 3D will be similar, but with much more terms. And the inner product that I have defined satisfies this. It can be checked, not that hard, but not hard to do that. Okay. Now let's go to the formulations. So we have summarized the calculus. So now formulation. So transport phenomena. Model formulations. So first, let's recall the continuous and smooth one. Recall the smooth one, EC1, EC formulation. So we have first to set up. So first set up. I from some t0 to infinity time interval. M is the manifold. So M smooth compact oriented smooth manifold, compact oriented Riemannian D manifold. D is integer, of course, and this is the body, the space domain of the body. Okay, and then this is maybe the setup. Okay, we have the M is GD united with GN. So these are Dirichlet Neumann boundary. This is the what space we have. So we have time interval and some domain with boundary, which is divided into two parts. The second, we have known variables, so known variables. We have Q. I will not write this time the dimensions, the physical dimensions, like length times. They can be found in the article. So Q is amount, like energy, charge, and so on. Mass, charge, and volume. If you have some fluid moving, it can be volume. Small q is, oh, this is not known. Sorry. Yeah. We have maybe V is omega d minus 1m. This is volumetric flow rate. This is not flux because it's not a density, it's exactly d minus 1. So how much volume travels through through surfaces? So this is volumetric flow rate. We have F in omega dm. This is internal production rate. We have so GD is in omega 0 of gamma d. This is, of course, smooth functions on gamma d. Maybe not smooth, but let's say smooth functions. So this is from gamma d to r. These are Dirichlet boundary condition. And in continuum is also given as a function because this is a d minus 1 form, but on the boundary, and the boundary is d minus 1 dimensional on the Neumann boundary. But it's naturally the flow rate through the boundary. So this is not Dirichlet bound. This is not the boundary condition. This is prescribed potential. Its rho is Dirichlet boundary condition, but this is prescribed potential. And this is prescribed flow rate. We have also initial temperature in the transient problem. Everything is from I just totally messed it up. This here is only for transient problems. For it should be from I to here, from I to here. Yeah. Let's remove that here. So from I to omega 0 gamma d. Everything can be dynamic, but the initial temperature is not dynamic. So this is omega 0 of m. This is initial potential. I think this is what we need. I hope I don't forget anything. Oh, I need also the material parameters. So we have kappa. From E d minus 1. So it's a transformation of d minus 1 forms, time dependent. Maybe it doesn't depend on time, but who knows? And it's dual. And it's dual sigma I omega 1m 1m I omega 1. These are conductivities. So this is conductivity. I find out that on Wikipedia there's an article and they call this transport coefficient. But let's, and this is dual conductivity. And we have the we have the capacities. And P tilde constant omega 0 and 2 C omega 0. And these are capacity and low capacity. So these are known, this is the input for the model. Of course, this is optimistic to have everything infinitely smooth, but in the discrete case, you don't have problems with different types of smoothness. And 3, we have the unknowns, unknown quantities. So we have Q, this is amount. I will not write again all the 4 types. We have small q, which is q d plus q. A is omega d minus 1. Sorry. This is from I to M. This is from I to omega d minus 1 M, and this is flow rate and diffusive plus advective. We also have temperature, the potential, temperature, pressure, so on. Temperature, doesn't matter. Just these are examples. We don't have any other unknowns. Yeah, and 4 governing laws. We have dq dt. This is in differential form. Is f minus dd minus 1 of q. This is considered a continuity equation. Q d is kappa delta d minus 1 d star of star 0 of u, but this is sometimes given as minus, I think, minus kappa tilde of, no, the different direction. This is given like star 1 of kappa tilde of d1 of u. This is how it's called, and just constitutive, maybe low, but it should be relation. It's not a fundamental.
D0.
QA is star DQ wedge with start with V. So this is subvection. And we have the boundary conditions. So the trace of Q on the boundary, the trace on d-1 forms of Q is Gn. This is Neumann boundary. The trace on 0 cells of U, this is restriction, is Gd. This is Dirichlet boundary condition. And trace the initial temperature U0, U of T0 is U0. This is initial condition. And it's time for the break, I think. Okay, I'm adding this